We are in chapter 4 where we are discussing bending. This is the 24th session overall and the 8th session in bending. Here we discuss singularity functions. This again is the overall roadmap of the first 4 chapters. Singularity functions is the last main discussion on SF and BM diagrams before we start looking at stresses. Now, this diagram gives a typical problem that we have dealt with till now. This beam is subjected to different loads as well as different types of loads. Normally, we have considered portions in the beam where the pattern of loading does not change. So in this beam, we considered PA, AE, EF, FB, and PG. We have then taken sections in these portions. So here we have taken 5 sections. We have found out expressions for shear force and bending moment at these sections. These expressions has been found out using x, which is an arbitrary distance. We have then found out the variation of shear force and bending moment for each of the portions by varying x. Thus, we have found out the shear force and bending moment diagram for the whole beam. Now, instead of dealing with 5 expressions for 5 sections, it would be easier if we can give one expression only for the whole beam. Thus, we can give one expression for shear force and one expression for bending moment. This is done by using singularity functions. Now, this point load causes a discontinuity in the loading. Can also be considered to cause a singularity. Singular functions are discontinuous functions at singular points. Now consider this function. These brackets are known as singularity brackets. If x is less than a, then fx is equal to 0. If x is equal to a or greater than a, then fx is given by normal bracket x minus a. Now consider another function. Here n is 0 or any natural number. Then for x less than a, fx is equal to 0. And for x equal to or greater than a, fx is given as normal bracket x minus a to the power n. Here we have separated natural numbers and 0. For 0, for x less than a, we get 0. And for x equal to or greater than a, we get 1. We can see that with the singularity function, the function does not come into play as long as x is less than a. can be considered dormant at this stage, but as soon as x reaches a and becomes greater than a, the function comes into play. Now consider this beam and the sections 1, 1 and 2, 2. Considering from the left in section 1, 1, P does not play any part, so the shear force is only Ra. However, as soon as x becomes a, P comes into effect. So we can see that the singularity function can be used in this problem. The shear force is given by this expression using singularity function. When x is less than a, then this portion is dormant and we get Vx is equal to Ra, which is what we have got if we took a section 1, 1. For x greater than a, this second term becomes P. The singularity bracket turns into normal bracket. If we consider section 2, 2, we get the same expression, that is Ra minus P. The expression for moment using singularity functions is given here. When x is less than a, then this portion is dormant and we get mx is equal to Rax, which is what we would have got if we considered moment in section 1, 1. For x greater than a, this bracket turns into a normal bracket and mx is given as Rax minus Px minus a. This is the same expression we would have got for moment for section 2, 2. So here with one expression we have given the expressions of two sections. Similarly with moment, with one expression we have given the expressions of moment for two sections. The singularity function is differentiable and integrable, similar to the x minus a to the power n within normal bracket. Thus, for n greater than or equal to 1, we can differentiate using this expression. And for n greater than or equal to 0, we can integrate using this expression. Earlier, while discussing UDL, shear force, and bending moment, we came across differentiation and integration formulas. So we can write expressions using singularity functions and differentiate and integrate as per those formulas. Here we have given a table for different types of loads and represented the shear force and the bending moment in terms of singularity functions. For each type of loading, We have given the singularity functions we use graphically. We have already discussed a point load. This function, where x minus a within the singularity bracket is raised to power 0, is also called a step function. For a point load, it is used to represent shear force. This function with x minus a within the singularity bracket raised to the power 1 is called ramp function. For a point load, this function is used to give the bending moment. Here we have a uniformly distributed load that starts at a distance a and runs through the entire length of the beam. For this case, we use these two singularity functions to give shear force and bending moment. Consider an x greater than a and these two brackets as normal brackets. Then we'll see that these two representations are the proper representations. For a triangular load, these are the singularity functions used to give shear force and bending moment. Again, if we take x greater than a, then you will find and consider that these two brackets are normal brackets. Then one will find that these are proper representations. There's a moment acting. We use the step function to give the representation of bending moment. Here we have given representation of shear force and bending moment in terms of singularity function for two distributed load cases. So these are the representation of shear force and bending moment for a distributed load that starts at A and stays there till the far end is reached. These two expressions are representations of shear force and bending moment for a triangular load that starts at A and stays there till the far end is reached. We'll discuss other cases of distributed loads later. Here we make a problem and solve it using the normal method as well as the singularity method. This will help us compare the normal method to the singularity method and show the efficacy of the singularity method. To start with, we find the reaction at A by taking moment about the point B. So Ra into L is equal to E into L minus A plus W into L by 2 into L by 4, which gives us Ra. We have three different patterns of loading in three different portions of the beam. So we take the three sections as shown. With section 1-1, the shear force is Ra and the bending moment Mx is Ra into x. Section 2-2 is any section between A and L by 2. The shear force here is Ra minus P, and the moment is Ra into X minus P into X minus A. The third section is between L by 2 and L. The shear force is Ra minus P minus W into X minus L by 2. The moment is Ra into X minus P into X minus A minus W into X minus L by 2 into X minus L by 2 divided by 2. So we get equation 6. We'll now represent the shear force and bending moment on this beam by singularity function. If singularity function, we consider a section as 3, 3. So this is the shear force given using singularity function. We earlier saw that this is the way a point load is represented, and this is the way a uniformly distributed load is represented. Now consider X to be less than A. Then the second term here and the third term here is dormant, so they are 0. Vx is equal to Ra, which is what we find here. Consider X greater than A but less than L by 2. Then Vx is given by Ra minus P normal bracket X minus A to the power 0, or Ra minus P, which is what we have in section 2.2. Now consider X greater than L by 2. Then Vx is given by this expression with the singularity brackets converted into normal brackets, which is what we have here. Now for moment, earlier we found that for a point load, this was the expression using singularity brackets, and for a UTL, this was the expression. For X less than A, these two are dormant, and Mx is equal to Rax, which is what we have here. For X between A and L by 2, we have Mx is equal to Rax minus P normal bracket X minus A, which is what we have here. Now consider X to be between L by 2 and L. Then Mx is given by this whole expression with the singularity brackets changed to normal brackets. This is what we have here. We can also get the expression for moment by integrating the expression for shear. Till now, when discussing distributed load, we have dealt with problems such as this. So here the distributed load starts at the point B and stays there till the end. We have given shear force and bending moment in terms of singularity functions for this case. Here, the uniform distributed load ends before reaching the far end, giving the shear force and bending moment in terms of singularity functions for this case is more involved. So here we'll discuss these type of cases. Consider a beam on which a point load has been applied. If we take a section 2-2, then both for shear force and bending moment, we have to consider Ra and P. As soon as we cross point P, the effect of P comes into force. A shear force and bending moment for such a case was given by these expressions. For a distributed load that starts at E, which is at a distance A from the left end and continues through till the far end, the shear force and bending moment using singularity function was given by these two expressions. So with a singularity function, we can start an effect at an intermediate point in a beam, but that effect stays till the end. As such, we can say that we can start an effect, but we cannot stop it till the far end is reached. That creates an issue for this type of problem where the loading terminates before the far end. We circumvent this issue by considering an equivalent loading as shown here. Here, both the loads on the top end and the bottom end extends to till the end of the beam. So we can give singularity functions for these two load cases, and as such for this beam, which is equivalent to this loading. The shear force for this loading in terms of singularity function is given by minus W singularity bracket x minus a and plus W singularity bracket x minus b. The second one is for this load. The moment is given using singularity brackets as minus for this load because it creates an anti-clockwise moment, and plus for this load because it creates a clockwise moment. We can have other types of loads such as a triangular load or any other load variation that terminates before we reach the far end. We then have to find innovative ways of representing the loads in terms of loads that reach to the far end, as we have done here. In general, therefore, singularity functions make the process of finding shear force and bending moment easier. However, when we have distributed loads that terminate before reaching the far end, special consideration is required. This is a cantilever beam which is subjected to a uniformly distributed load. We'll solve this problem using both singularity function and the relationship between UDL, SF and BM. This uniformly distributed load ends before reaching the far end. We have therefore used equivalent loading. Here there are two uniformly distributed loads which both extend to the far end and is equivalent to this problem. Since both the UDL extends to the far end, they can be represented by singularity functions. Here the second term represents this load which starts at a distance a from the left end. The shear force at A is 0 and we can find Vx by integrating minus omega x. So this is the expression for Vx. Also the moment at A is 0 and we can find mx by integrating the shear force. So this is the expression for the moment. Now find the shear force and moment at B and C. At B, x is equal to A. So the second term here is 0 and we get Vp as minus omega 0A. Also the second term here is 0 and we get Mb as minus omega 0A square by 2. At C, x is equal to 2A and substituting 2A in this equation, we get Vc as minus omega 0A. Also substituting 2A in this equation, we get Mc as minus 3 by 2 omega 0A square. We now develop the shear force and the bending moment diagram. Both at B and C, the shear force is minus omega 0A, which we have plotted here. So the shear force is constant between B and C. Since there's a uniformly distributed load acting between A and B, the shear force is given by a straight line. At C, bending moment is minus 3 by 2 omega 0A square, and at B, the bending moment is minus omega 0A square by 2. So we have plotted and joined them by a straight line since the shear force between B and C is a constant. Between A and B, the shear force variation is linear, and as such, the bending moment variation is shown as quadratic. The magnitude of the shear force increases from A to B, and the slope of the bending moment diagram is shown as increasing from A